Okay, hi. As you just heard, my name is Kirchner. I'm studying at the University of Freiburg, neuroscience, and I have two occupations. By day, I'm working for the FBI, which is the Freiburg Brain Imaging, not really like the Federal Bureau, but it's still pretty cool. So there we do fMRI studies and imaging, and by night I'm a mathematician, and I derive theoretical results about neuron models. And I want to talk about a little result here that I derived. And it's going to be a little bit technical, so this is probably for like the mathematically inclined people out there. But I'm also really like keen to talk about the intuition and about the implications with you if you come to my poster. So the model that I'm considering is this one. It's a point neuron, but it's not the classical point neuron. In the classical point neuron, all the synaptic input is just integrated, and then maybe you have a leaky term or something, but it all kind of accumulates. Here we have the stochastic input not directly to the voltage, not to the membrane potential, but to the conductance processes. So we perturb the conductance, and this is not a model that I come up with. This is like one of the classical models that are out there in the literature. And you can see the model equations on the left-hand side. And one of the cool features that this model has is a non-monotonic response function. So if you bombard it with excitatory and inhibitory input, then the free membrane potential actually stays the same because you put like inhibition and excitation pretty much equally. Configure there. So this should be like, yeah, this is the free membrane potential. You can't really tell it from the label, but this is as constant as it gets. There's like a small dip there, but that's not important. And while this free membrane potential is kind of constant, our variance is non-monotonic. So it increases and then it decreases for higher input ranges. And this is also something we observe in neuroscience and biology. So our neurons, they respond non-monotonically to input. They have a certain frequency tuning. To some frequencies, they respond more than to others. And this behavior is reproduced by the model. But now we have a problem. We don't really understand why the model manages to capture this. We don't really have a mathematical proof. We can simulate it. We can make some strong simplifications to show this, but we don't really have a full mathematical theory to show why this model produces this behavior. And then the model is, I don't know, not completely useful. So that is where my work comes in. I don't give a full mathematical theory of how this works. I make an approximation, which works pretty fine in the end. So I use a theory called the large deviation theory. This comes from statistical mechanics originally, and it's all statements of this type here. You have a limit where we describe the cumulative distribution of, this is the first exit time, and it depends here in the limit of a small noise. So if our perturbations are like neglected on this right-hand side. And the small noise limit, it might be a bit unintuitive why we would want to take a small noise limit if we are actually interested in the regime where the noise gets very large. But as it turns out, the results, they still hold even for larger noises. So basically what it all boils down to, I'm not going to walk you through the equations. We have to determine the most likely way in which our desired very unlikely event is going to happen. So we're all talking about unlikely events, namely that the membrane potential reaches the threshold, which is, it's a fluctuation, it's not the normal behavior that we would expect. And then we look at what is the most likely way that this can happen. And I didn't talk about that graph, that was there on the slide because I don't have time for that. So these are some sample realizations of how these trajectories can look like. In gray, we have the membrane potential and it approaches the threshold from below. And in this work, I derive the equation for how these gray trajectories have to look like. Then I can plug these trajectories back into the action functional. I get some kind of cost. I get the how much control, how much synaptic chance has to accumulate for this event to happen. And if I do all of that, I get a nice expression in the very end, which is something like this. And this one is non-monotonic. It's, for example, this red line that you have up here. That is 1 over the line that we have over here. And this is the non-monotonic thing that I wanted to show in the beginning. I think you all got that, right? That wasn't too difficult. Yeah. Well, I guess 6 minutes is really not enough time to like go into the details of the derivation, but I'm super happy to talk about this with the people who want to come to my poster. And with this, I want to thank you for your attention, and see you around.